Hey everyone. Today we're going to take a look at all the ways that we as humanity have looked at light since our inception. We're going to start with the simplest models, look at ways that we've needed to complicate those models as behaviors have gotten more and more complicated and observations have gotten more and more ample. And then we're going to look at Albert Einstein and what he did to win his Nobel Prize. So, without further ado, let's get started. Right. So back when the Greeks were very first learning about light, they used what we're going to call a ray model to discuss light. And the ray model is very, very straightforward. They basically thought of light as a laser pointer. So light travels in straight, coherent lines. And that worked to describe a lot of the things that they saw around them. And specifically, there are two behaviors of light that they use this to explain. The first one is reflection. And reflection, just like you think of when you have a mirror, reflection is the bouncing of light off of a surface. And the ray model works really well to describe this. We're able to actually see that these two angles end up being equal and perfect fit. The other behavior we see is refraction. Now, if you've ever seen somebody standing in a pool and you're outside the pool and their lower half looks like weirdly short, that's because of refraction. And refraction is the bending of light due to a change in medium. So if we think about light moving from the air, where light moves quite quickly, into, say, the water, what we end up seeing is that the beam of light bends. And we can talk about a couple different reasons around how to understand this. It actually turns out the Ray model doesn't provide a great explanation. Let's talk about an analogy first. And then when we get to one of our later models, we'll come back and think about an actual reason. And so a good analogy for this is think about a lifeguard at the beach. Lifeguard is up in his hut and he sees somebody out here drowning. Now, that lifeguard has a couple of options for how to get to the drowning person, but he has a problem. He is a much faster runner than swimmer. And so he thinks about a couple of options, right? So he could run straight to the water and then swim all the way out. Terrible idea, because if he's not that good at swimming, you don't want to be doing it for that long. Maybe he could run all the way as far as he could until he has to swim. Unfortunately, this is also a pretty terrible idea because it turns out he goes way far out of his way. Maybe he could go the most direct distance. But again, that gives no priority to the thing that he does better, the running, over the thing he does less well, the swimming. So it turns out, and you can actually show this mathematically, that the best route for him to take is exactly what we've traced here, that he runs a little more than halfway and then turns and swims out the rest. And this is the fastest way for him to get from his lifeguard stand to the person in the water. And so for a long time, people just thought that light was doing what was quickest, what was the easiest and fastest thing to do. Um, these two behaviors very easily described through the Ray model. Refraction, for the record, we can come up with a relationship between this angle, what we call the incident angle, and this angle, the refracted angle. And that relationship is called Snell's law. Uh, and it has to do with how quickly the light moves through each of those, which we are going to encapsulate that here through N, which is the index of refraction. And it's basically a measure of how quickly light moves through that material. So up until from kind of ancient times up to about 1800, this is how we think of light. And then something happens. One day, a scientist is sitting in church because around the year 1800, that's actually something scientists did quite a lot. In fact, historically, a lot of the people who had the most time to undertake scientific investigations were actually members of the church or clergy. Think about like Gregor Mendel, who invented genetics. He was a monk. But he was sitting in church one day and he saw light coming in the window through a stained glass window and shining on a spherical object. Now, if you're like me, your expectation is that that's going to create a spherical shadow or a circular shadow. But instead, right in the middle of that shadow, there was a spot of light. And this scientist fairly freaked out. We call this the Poisson bright spot. You might also hear it called the Fresnel bright spot or the Arago bright spot. And it breaks physics because that's not what we would expect rays to do. We would expect these two rays maybe to come through around the light, but we would expect there here in the middle to be a dead zone, and there isn't. So in 1800, we had to rethink light. And what they noticed is that this behavior, this bright spot, actually looked similar to some other patterns that scientists had seen for other types of motion, and specifically for waves. So scientists decide in 1800 that really maybe light acts more like a wave. And this helps us understand two specific behaviors: diffraction and interference. So diffraction, and by the way, if you want to go look at my earlier wave model video, you absolutely can. I talk about both of these in there. But diffraction is the fact that waves can bend around objects and that they spread out. So think, for instance, if you're at the beach and you see a obstacle in the water and you have a wave hit that obstacle. Maybe it's a rock, right? Yeah, the wave will split up for a little bit, but eventually it'll come back together. So you get this like dead zone here, right? But eventually the wave comes back together. That's not what we would expect to see if we had just like rays or particles, point masses, any of those things moving. We'd expect to see a much, much larger dead zone that went on kind of forever. And so this property of diffraction is exactly what we need to explain the Poisson bright spot, because essentially what we're seeing is that coming back together of the light, and that's why we get this bright spot. The other thing we get is interference. And interference is how one wave and another wave can, when they are in the same place at the same time, either amplify each other or deaden each other, creating, when we talked about with sound, loud and quiet spots, but also, in the case of light, bright and dark spots. And so, in fact, if you shine light on a screen, you end up getting a two-source interference pattern, exactly like what we saw with sound. Now, we will come back to this actually at the end of the unit, and we will listen, we'll read a book called Quantum, A Guide for the Perplexed. Um, I want to put a star on this because this actually ends up being a really hard thing for us to explain later on. Um, but for now, let's say works out pretty well. Diffraction and interference are explained through the wave model. And scientists for a second kind of worry because, well, I can explain those through the wave model, but what about reflection and refraction? Because after all, like scientists really do want one model to explain all of light. And if I have to have the ray model for the reflection and refraction and the wave model for diffraction and interference, that makes me a little hesitant. Um, but luckily, as scientists think about this a little bit more, they're able to make sense of it. So I am going to switch us up here. Right. So here we see a simulation. This is from PhET at Colorado. Great site. And this is what you get with like light as a ray, right? So we get some refraction. If this is glass, is what we're supposedly dealing with here. You get some reflection as well. But they start thinking about like, well, what about a wave? And so if we think of light as a wave, right? So we've got like kind of highs and lows here of that wave, the peaks and the troughs, as shown by red and black. To understand refraction, basically understand that this part of the wave, this lower part of the wave, slows down first, while the upper part of the wave is still moving quickly. And as a result, you get this turn downward. It actually works in reverse too. If the top part speeds up first versus the bottom part where it's still going slow, it will also produce the correct turn. So for the first time, not only does the wave model explain all the behaviors we want it to, it also gives us a better understanding of the why, rather than just saying, well, we don't know why the light needs to move as quickly as possible, but it does. Here we get a really good understanding of why. Also, this explains refraction, right, or reflection. This part bounces off and becomes there, whereas once this part gets there, it also bounces and we get reflection. So scientists are super excited because they think from about 1800 to about 1904 that they've got it all figured out. And so um, they have decided they are all in on this wave model. But alas, because right around 1904, a scientist named Max Planck makes an observation that creates a real problem. And that is something we call the ultraviolet catastrophe. This is my future band name, patented. You can't have it. All right. And to put it simply, the ultraviolet catastrophe says that we expect ultraviolet waves of light to have a certain energy, and they don't. That is a vast oversimplification, and if you want to get into the black body radiation and everything that goes with it, please feel free to do some research on your own. But essentially, we expect, due to the wave model, that UV radiation has one level of energy, and it doesn't. So there is at least one observation now that we can't explain using the wave model. And so scientists think, and they realize that there is a model that explains the amount of energy UV radiation has. And that is something called a particle model. So what if instead of viewing light as a coherent uh, line or as a wave, what if we view it as a bunch of particles, almost like atoms? And we call these photons. And at this point in time, a scientist you've probably heard of decides he's going to pick this up, and that is Albert Einstein. And specifically, he decides that he's going to use something called the photoelectric effect to prove once and for all whether light acts as a particle or as a wave. And the photoelectric effect is something that to us doesn't sound all that surprising. And it's amazing how far we've come since 1904. But essentially, what people had just started to notice was that when you shine light on certain materials, you get a flow of electrons, electricity essentially, out of the material. I mean, this is a solar cell, and for us, it's not that surprising. But for them at that time, it was shocking. And so we knew that obviously this material had atoms, and each of those atoms had electrons. And so something must be happening within the metal to free up those electrons and let them move through a circuit. And so Einstein decided that he was going to use this setup. And he thought about it this way. He thought that if light is a wave, then energy is being gradually delivered because that's what waves do best. And eventually, enough energy is delivered to free an electron. But if light is a particle, then what we should be seeing instead is that the photons, those particles of light, collide with the electrons and knock them out of the material. So essentially, he sees this as a difference between a gradual process and a sudden process. And so he decides that there are 3 observations that he's going to do, and that between these 3 observations, he should be able to determine whether light is acting more as a wave or as a particle. So observation number 1, he thinks about the time delay. And he thinks if light is a wave and the energy is being delivered gradually, then it should take some delay before you get your first electron. And that we could probably play around with the energy of that light and make that delay longer or shorter. But if light's a particle, then we would not expect to see any delay because the second that first particle hits an electron, it'll knock it out and we'll be on our way. So that's the first observation that Einstein's going to make. Second observation is what we call threshold frequency. And Einstein says if we have a low frequency wave, which would make it a low energy wave, then it doesn't matter. Like, we'll still have a big time delay, but like eventually any wave will still be able to deliver enough energy to free an electron. So he says that any wave can free an electron. It just might add to the time delay. But if light is acting as a particle, think about the electron as, let's say, a softball. And if I have a really, really, really low energy photon, maybe like a scrap of paper, a little ball of paper, and I keep throwing it at that softball's never going to move. I need a higher energy photon, maybe a tennis ball or a bowling ball, to throw at that softball to get it to move. And so he says, like, low energy particles would never free an electron. Finally, intensity. And if we think about an intense wave, we're thinking about a taller wave, wave with higher amplitude. And he says that that would lead to an intense light would lead to faster electrons because you're still focusing on one electron at a time, but you're just imparting more kinetic energy into it. But if we think about what intense light would mean if we we're talking about photons, a wave or a particle model instead of a wave model, we would have more photons, in which case intense light would end up with more electrons freed, not electrons freed at a higher speed. So are we seeing more electrons or faster electrons? And he thinks that's going to be a pretty important distinction. So he does these experiments. And I have to say, like, I think a lot of people, when we look at this history of light, I think a lot of people are like, well, why didn't we figure that out sooner? Well, think about what else is happening specifically in this like 1800 to 1900 range. This is the first time that we're getting electricity, electric lights. These things are becoming more prominent. Up until then, you had to work with daylight or like a dim candle. And so you couldn't really do experiments with light. Additionally, those electronics are letting us have much more sensitive measuring tools that go to many, many more decimal places. And that's exactly what Einstein needs to do this experiment. So he does the experiment, and what does he see? He sees no delay. He sees there is a threshold frequency. Under a certain frequency, light never, ever, ever creates electricity. And he sees more electrons, not faster electrons. So he comes out of this and publishes a paper in 1905, which we actually in science call the Annus Mirabilis, or the miraculous year. Einstein publishes several papers this year. One of them goes on to become relativity, and one of them goes on to become this. And this ends up being what he wins his Nobel Prize for in 1922, because it ends up pointing us towards a particle model. But some of you are probably thinking, so how do I explain diffraction? And how do I explain interference? And the answer is you can't with a particle model. And that's what's so groundbreaking here, is that for the first time, we have to accept that one model will not answer these questions. And so this is the beginning of what we call wave-particle duality, which simply put is the idea that light is neither a wave nor a particle, and both a wave and a particle. It acts as a wave in certain circumstances, like when we get the Poisson bright spot, when we get diffraction, when we get interference. But it also very clearly acts as a particle in some cases, as it did in the photoelectric effect. And this is groundbreaking. And to me, this is a really interesting part of science. And it's one of the reasons I teach this, even though it is fairly advanced science, is because this is basically when we as a society start to shift away from what we would call like determinism, which is Newton's view of physics. With enough equations and enough data, we can predict anything, to a more probabilistic, or what we might call stochastic view of the world. That the world is full of chaos and randomness, and that we may never fully understand the world. And I think that's a really cool thing. And if you like the determinism of Newton, like engineering is a great field for you. Like I say that as somebody who has two engineering degrees, like it's a great place to do the equations, get the data, make the predictions. But if you're thinking of being a physics major, you would like this. You would enjoy that there's still questions here and that there's still things we don't understand, and that one model that the human brain came up with cannot fully explain the miracle of light. All right. Thanks so much, everyone. Have a great day. Bye.